Hello everyone. This is gonna be a slightly unusual stream. I just want to make a tiny bit of progress outside of my usual hours, but since this is not one of my regular stream days, I have none of my usual setup. So today is gonna be no camera and slightly lower effort. I am mostly gonna be trying to do some code cleanups and documentation today. If you haven't watched this week has been a source of a lot of progress. We have been working on the code generation all week, and yesterday we finally did a run of the entire compiler. There's so much that's missing, there's so much that's not there yet, but we started with a file like this one containing main and a function call and a recursive function, and we compiled it down to a Piètre program like so. So that is a pretty significant milestone, even though a lot of stuff is still pretty broken. So today, I think a short stream, no camera, and just gonna be doing some cleanups. Especially when I did plug things in at the last minute yesterday to try to get some images. Some parts of the linking and assembly were kind of a bit broken. So I think I'm gonna start with that. Specifically, I think I want to split this linking thing. I probably want to start moving some of the stuff away right there. Okay, I had started doing that yesterday and I did not keep it. Partly because it will allow me to remove some of the lenses that are here, which are making this module a bit of a pain in the ass. So this should be should be enough. That's the linker state. I will probably want to add a few more extra things. Specifically, I think I want to hard code rather than let it be a like something that is unclear. I want to make very clear what the main address is. And that is going to be because now main is the address 1 in the program, which means that when we start the program, we jump to address 1, which is this one. The problem with that is that this function, this main in the code, returns at some point, and I don't have an easy way of capturing the fact that the main may return. So I will want to introduce a start function that calls the main and does handling of termination of the program properly, which means address 1 will not be the address of start, it will be the address of the main provided by the user, which means I want to distinguish between where main ends up being. And I suppose I don't have actually to hard code it, but I think, yes, the idea is this, whatever the linker returns will have to capture that information. And I think it just means that the current needs to start at 3 because addresses 1 and 2 are reserved for the start function. So maybe I want to name that so that it's extremely clear and add a comment. Okay, something along those lines. Now, what do we want to move away from this? Linker M is no longer required. Initial state no longer required. All of this can move away, which means this file now just has this visit function, well, which is just an implementation detail. We will want to Now we can just move this to the top, which is the top level function. Linking will take a hash map from name to the instruction unresolved. I have actually changed the type. This is now an instruction buffer. Where did we introduce that type? Did we introduce it as part? I try to avoid having a stage of the compiler do an import of a previous stage of the compiler. So let's see where we have defined the instruction buffer, and maybe let's move it into a representation part of the code. This would be where is that defined? Oh, there we go. So in the monada. Okay. So I will probably want to change that. Change this type. Move it elsewhere. Where would it go? Probably in representation somewhere. I suppose in bytecode it makes sense, since bytecode is what defines what an instruction is. It doesn't shock me to have here that an instruction buffer is a sequence of those instruction unresolved. Okay. I will probably also want to have in the representation after the bytecode, I do have image here. That is not really useful. I don't think this is used. I probably want to start putting the idea of like the way data is stored across things is stored in representation. I might want to put some stuff there, such as the output of the linking phase that is used for the input of the assembly phase, which for now I just use a very ad hoc type, which is not very elegant. Maybe instead I want to have here something like the link output. Well, is that, how do I name this? Link output is horrible as a name. Is that the binary that we make the image out of? Kinda, I suppose. Which means this is probably belonging better in a binary file rather than an image file, which means I'm gonna delete image. What will a binary contain if we look at the linking process? It contains this at the moment, which is not great, but we can do better. We can do better than that. So this would be that would be the main address, which we are not gonna export that away from the, like, it's gonna be part of what the linking phase outputs, which is gonna be an int, which is where to start when we do the assembly. And there's gonna be binary functions, which is gonna be a sequence of compiled function, I suppose. And a compiled function is going to be instructions, which is a sequence of instruction. How did we name those? Bytecode. Is it resolved? It is resolved. So that's the instruction, the equivalent of instruction buffer, but post link information. And I need, for the assembly, I need to persist another thing, which is the entrance count, which is an int. Which is what this int here is, basically. Okay. So with that done, I will need, of course, to import bytecode. I will need to know about the bytecode. The linking phase will now give us a binary in the output. Takes a bunch of modules, but at this point we only take the instruction buffer and the names. So this is basically the big collection of all the functions. I suppose we could still at this point take something that is a bunch of modules, but I think this is like a reasonable interface. And which function is the main, basically. Okay. I'm gonna go back to the monad. Here I'm gonna introduce run linker that's gonna given a hash map of address to int will and a action in the link monad will give me that value. Maybe I need the result and the final state, so let's do that. So this is gonna give me the value and the final state, which is a linker state. Run linker is just basically a flip run state, I think, of initial state. I think that should be enough. Oh, except since I have lenses here, the order of declaration matters in this file. Therefore, I need to put that I need to put the run linker below those things. That's fine. Which means now this becomes run linker of this Oh, I don't need the... Why do I need the... Oh, I need the final state to do this, of course, yes. And then I can do that. Okay. Or maybe let's do it this way. It might be cleaner. Okay. Next, what do we have to change? Because we have a bunch of things to change. So visit is a function that looks... So this is already completely wrong, actually, good to think of it, because I have changed the way we output things. We don't just output a list. Now we have a proper binary of things. So that means I will need to start with, like, the output of this is going to be a binary of some kind with the binary main address being the main address we have defined here. So the first addressable entrance. And with the functions. And the functions are going to be what we had called result before. This is going to need to be a sequence of things. Run linker hasn't changed. Interesting. Here I was always visiting main first, that it would always be... I still think I need to do that. I don't, in fact. I don't need to do that, because I wanted main to always be the first function on the left-hand side here so that it would always get the address 1, basically. But I don't need to do that anymore because now that I'm giving its value here, I could instead, while I address the things of main, just look at what value I have given for that, which would mean which would mean um that this is wrong to start with, of course. But this is going to be main address, I suppose. But the upside is I should no longer need to do a special case of this like I've been doing, which is nice. What that means is I should be able to do a very simple traverse with visit of the hash map, which is the functions. Because visit doesn't really need their name. That gives me a hash map from name to whatever this function will return, which I assume for functions will be what we need, which is a compiled function, basically. And I suppose I could then just add here function entrance, which is the address of that function's entrance, basically. Now, if I do that, that means after I do this, I have all of my compiled functions, which is a hash map. I can get the main address by doing by looking at my compiled functions, looking for the one that has the unique name for main, and then getting this function entrance thing. Perfect. And now what I need to return I think I'm just gonna change. No, I still need to do this functions final state because I need to introspect this thing from final state. So I'm gonna call it result again, move this back as result, and here return some kind of binary main address and functions. And the functions here is gonna be a sequence from list of, and I think hash maps have a I want the keys. There we go. It's going to be a list. This is going to be the key. Sorry, not the keys. The LMs of the compiled functions. So I look at this hash map. I get its values. It's a list. I make the sequence. And I give it to my binary, which requires a sequence of compiled function. Okay. And now I have my main address. So now the only thing I need is to make a compiled function. Compiled, is that the right word? Do I really want to use that word? I suppose as the output of the linking phase, not the worst. Do I want to call it a symbol? Do I want to call it a function? I kind of want to call it a function just because that's the name I've used for at every level. And I will have to disambiguate which function I mean, but I think as part of the binary, this is a function. I think this makes more sense. And I don't know if I need lenses for those. We'll see. Probably. Actually, I could probably just do it right now. Here I can remove template Haskell. In monad, I need to put it back. Okay, no, I'm just gonna rewrite it. I'm gonna put it there as well. I don't know if I need it yet, but just in case, this is a small module. This will not add a lot to the compilation time. Okay. And so visit will be my main thing. This is going to be the function that, given an instruction buffer, gives me in my linking monad a function. And I want to be very clear that this is qualified as binary. Or I've used 2-letter abbreviations so far. I mean, not qualified, just as, in case this needs to be disambiguated. Okay. So now this thing needs to do the same thing we were doing before, which is do a linking process, which so far there is no reason to change. When I visit a function, I set the entrance count to 0. That makes sense. Then I traverse all of the instructions. Okay. So basically what this phase does is replace all the push address by a push int by looking an address into a hash map that we build as we go, hence the laziness and hence the fact that I am giving as an argument this hash map that comes from the result there. That being said, I think I want to move this particular implementation detail. I think I want to move it to the monad and hide it away. And I think I want to... instead do a reader T of the linker info on top of a state of the linker context. And those names is because every single other stage is using info for the reader and context for the state, I think, except maybe some exceptions. So I think trying to be consistent in the naming is, I think, a good thing. So the linker state is the linker context. And this remains more or less the same. Why do I use the registers for? Oh, this is where I record the things that will become a hash map later on. Okay. So this is the... register is a horrible name. Registry, I think, would be better. And the linker info will be the part that contains the addresses, and this will be the lazy hash map of address to int. Okay. There's probably a better way to do this than storing a list here. I want to be careful of the laziness and of not forcing the evaluation at any point. I wonder if I could just make this a hash map of address to int. I will wait until this works before actually changing that. So now what changes is the hash map doesn't need to be given here. Because I need to be careful here. Yeah, I don't need to be given this thing, so I have the action here. And then what I'm gonna do is basically the same thing. I get, so this is gonna be final state result. I'm gonna copy the thing I had before, where final state result is the result of running the action and flip run reader with the hash map and flip run state with the initial state, which will be something that I might not even need to name, but I think just initial state is fine. There we go. And here goes this part, which is making the hash map. Where is that again? There we go. Okay. And there's probably a way to just make that hash map directly and avoid keeping a list like this, but first let's make this work. So now the upside is I no longer need to. I can probably even just do that and say result here. And now this tricky thing where the result here is used as an argument to the action that gives it recursively, that is hidden from this part of the code. And this part of the code can just do run linker. And I think that's a bit better. Okay. Okay. We'll have to check that this works, of course, but that should be fine. Now, to get back here, when we visit a function, we set the entrance count to 0. That makes sense. We get our result, which is traversing this. So here, rather than the uses, the ls addresses, this has become a view. How did we call it? So that's going to be view li addresses. Okay. And this is now the registry. Okay. Everything else remains the same. And at the end, rather than outputting a tuple of this, we are outputting a function. And the function contains instruction entrance count and then the function entrance. So the instruction is the result, the total count is that, and it contains, I need to keep track of the first entrance that this function had. By definition, I'm going to assume that this is the first I encounter, and the first I encounter would therefore be the current. So that means function entrance is use ls current, which means this is here the function entrance. Okay, so that's a bit better. Hopefully, at least this module is cleaner. And now the big difference this makes is now in here, we will have a proper start function, and main may be arranged anywhere else. Maybe there's other functions before main. The order is no longer dictated with main on the left-hand side. It is left completely to the whims of the assembler at this point. Well, no, to the linker, because they need to be in order of address, I suppose. But I could absolutely make them at this point sorted by length or something. I could do that. That could be fun. Like here, I could traverse them and sort first the functions by length to make the image less lopsided. It's kind of tempting, but there's not really a point in doing that. So let's not bother. So that should be the cleanup of the linker. We can go now do a similar cleanup of the assembler. First, I don't know if I need a monad in the same way, but I do keep some assembly state, it seems. And if I am keeping some assembly state and I have some initial state, I am ready to bet I have a run state somewhere. Oh no, I don't seem to have a run state anywhere. I have an exec state. So okay, so I do have a monad somewhere in there, which means I could do the same kind of cleanup I've been doing for the linker, which is introduce a monad file here. Copy all of that. And that way now I have the lens stuff isolated in a file where the order is less a problem. Okay. I do not remember how this works at all. This was all written almost a year ago at this point. A bit less than that, because we started the project with the parser that took us a while. I think this has no business being here. I'm just gonna move this back here. So here, assembly state, initial state goes away. Make lenses goes away. We can bring the top level function to the top of the file. Oops. This needs to be just a call to monad here. So here, assembles takes as an argument a binary now. We've changed that. So representation binary is required here. However, I am going... Oh, hello, how are you? I'm going to need, and the whole point of this change, beyond just... Oh, no, just this was a slightly unplanned stream. I wanted to make some progress this evening despite the stream being unplanned. So I don't have exactly my usual setup because, again, unplanned. So it's a slightly lower effort stream during which I am not going to make big leaps in terms of progress of the code, but mostly cleaning some old stuff, adding some more documentation where required, and yeah, with not the usual setup, and also not being very presentable today, just camera off. So yeah, just a slightly shorter, slightly lower effort stream to do cleanups and documentation. Because it's the thing of like, I really have this strong self-imposed rule of I will not work on this project outside of the streams. I want all of the code to be on the streams. I think there's been 2 commits since the project has started that have been made off stream, and that's it. So I'm really trying to do that. The downside of it is when I want to make progress on things that are less flashy, I can't do that, an hour here and there. It has to be on stream. So those slightly lower effort streams are good for this kind of cleanup and documentation effort. I'll probably stop fairly early this evening if I have, because I might have other plans. So yeah, again, slightly lower effort stream. I've just done a quick cleanup of the linking phase, introducing new proper data types, cleaning a tiny bit the thing, moving some code around so that it's a bit cleaner, which is always good. And I have a fun thing in the linking actually, and I might use this to make it better, where I do some fun circular recursive programming where the linker has a reader that contains some info, which is a hash map of addresses to int, and the state contains a registry of mapping from address to int, and the reader is initialized with stuff taken from the state. So final state is the result of running this, but I'm taking the registry from the final state as an argument to the run reader. Fun circular programming. That works thanks to laziness. That's always fun. Okay, so yeah, I was here at this point doing a tiny bit of cleanup of the assembly. I've moved some of the code in the assembly monad folder, which doesn't have much, but it means I move the lenses stuff out of the way, which is always good. Because this is a template Haskell thing that generates some code for me at compilation time. Specifically, it generates lenses for this particular type. The big downside of code generation at compile time using template Haskell is that it makes the order of declarations within the file like it makes it matter. By default, a Haskell file, I can declare things in any order I want, but as soon as I have this template Haskell thing, the rest of the file has to be, like, the order of declaration matters, and it's really unpleasant, so I try to move the state stuff that declares the lenses to a separate file to be free for the main file here to organize things as it wants with the main entry point at the top of the file. So here I'll probably just want some kind of run assembly, which is gonna be taking my assembly monad, which I think, is just, or assemble, I think, if I want to be consistent with the rest of the naming conventions of this project, which is just gonna be a state monad over an assembly state. But the run assembly is gonna be taking some assemble of A and return A, I guess, and run assembly. Unless, no, I only care about the assembly state, which might be the case. In which case, run assembly is flip exec state with the initial state. And I will need to know what the color and image is from the initial state, I suppose. Okay, so I do use it per image. Interesting. Okay. Why do I have some very manual list handling here? Of course, yes. Yeah, that makes sense. This can probably be rewritten as trying to iterate on pairs of instructions rather than doing this. Because append instruction there. Because I'm iterating pairwise on the list of instructions, basically. I could probably generate something that does that for me, rather than doing this kind of like very manual list manipulation. Although I will need to make sure that I do include the Maybe this is not the worst. The reason why this is like this is because the size of a particular group of pixels sometimes depends on the further instruction. When I don't have a particular size, I just fill my function, but otherwise, the size of a block determines the size of a push. So when I have to push an integer on the stack, the size of the instruction actually matters. Okay, well, I'm gonna keep it this way for now, but I can probably initial state green, function template green. Okay. What is function template? So that must be a dependency coming from somewhere else. Oh, or is it in here? No. Huh. Did I change something in there? Did I remove something important? Let's see. I don't seem to have. So where is it coming from? Function template. Interesting. Just to be sure that I didn't mess up my... No, okay. Huh. Where could this be coming from? This is import qualified, so it's not... No, it's definitely coming from somewhere inside the... Oh, it's one of the templates. It's one of the generated templates. That's what it is. That's what it is. Yeah, there we go. Generate templates is here. And generate templates is defined in here. And this is the thing that loads those files at compile time, such as the function one, and gives me a template. That's what it is. I had forgotten this part of the code. I'm not going to touch any of this because so far it works. The only thing I care about here is trying to see when I go through a function. I'm going to move this function to the top. This is where I run the exec state thing. Perhaps that means I want to... Do I want to hardcode this here, is the thing. Like this initial state needs to know what the image starts with and what the current color is. This seems to be hard-coded to always green and of course the function template. I'm tempted to actually just make it hard-coded as part of this. Like, yeah, sure, the initial state is always, like, it doesn't change anything compared to what we have now, green. And this will be the image function template green. And I suppose I could just take a color as an argument, color, and make it the same in both cases. There we go. Which means now this takes a color here. And I can probably remove this initial state, come to think of it, and just make it here. Okay. Which means now this becomes here a run assembly of okay, so it's gonna be first I'm doing this thing where I translate any kind of push int into a series of add and multiply to make them smaller. Okay. I'm gonna call that resolve. This is an expand. Oops. The only thing is now I have a sequence rather than a list because I'm changing my containers. Does sequence have a concat map? Does it have concat at least? If it is foldable, it probably has concat map, right? It has fold map, which is the same thing. Wait, is sequence a monad? It is. Okay, so I can just do a concat map or a list comprehension. That will work. Okay, so first that means here our first step is instructions, expanded instructions is going to be the result of doing instructions into expand push. So this needs now to take a sequence because that's what we have changed. In fact, this probably takes a function now, which means the instructions are in fact the function instructions, if I remember correctly. Yep, F instructions, there we go. So now this returns a sequence of instruction resolved, which I can probably do. I might just use an extension of the language I don't have enabled by default because it can be annoying, which is the overloaded lists, which makes those list literals behave as like any type that has from list, in this case sequence. I suppose I can rename this just expand instruction, because maybe at some point some other instruction will need to be expanded, and it takes one instruction written as sequence. So this is any instruction that needs to be extended, then that's how it's done. And this remains basically the same in the case of In the case of a push int that's 0 or negative, we can't push that directly. We translate it into push 1, push n plus 1 subtract. Otherwise, just go with n, and any other instruction for now, there's no other need, so all of the others just return pure of the instruction. And this is our go recursive function. That looks good, I think. I probably need to try. I probably need to try more things when I debug this, but otherwise that should be fine. Okay. So we have rewritten this to be expand instruction concat map of the sequence of instructions in the first place. And run assembly needs a color. For now, that color is green, although we could change that at some point to be a determined color for each function or something. Doesn't make a difference. And then what do we do with this? We have this go thing. This is the thing again where we get pairs of this feel I want to avoid I would like to try to avoid having this kind of like manual list recursion. It always feels inelegant to have a manual list recursion, especially since now I no longer have a list recursion, I have a sequence. Is there a way in sequence? I imagine, is there a zip in the first place? Zips and zips, there we go. So a basic zip is probably what I want. Although, I need to check something. Does sequence... Which one do I have? Has the GHCI? Neither. So it's not gonna compile. Is sequence now generic over any foldable, or is sequence still on... It isn't traversable. Okay. 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 So I could be doing a thing. I could be doing a thing where I zip with go, which is going to be my local function. And what do I zip with? I zip the instructions, so those expanded instructions, and I zip them with sequence drop one of the expanded instructions, to which I add a return instruction, which is the most inoffensive I can imagine. This way, every instruction will be followed by its next that will get a list of pairs, but that will call zip with on all of them, and then the result needs to be sequenced to get a sequence out of this, which is what we want. And this is in fact a sequence underscore, and then I can return use current image. Okay. I guess this is the same, this sequence of the zip with is the same thing as doing a for zip of the thing. Yeah, I think this is fine. Okay. So now I can remove this, and now go is a very different function because go takes an instruction I and an instruction J, kind of this in the same way, but all of this recursion stuff is no longer required. It's handled for me. And now this is purely, is this a push int of n? In which case this is append instruction just n of I, or is it, well, I can even rewrite this as go for a given instruction is case of the following one of, if it's push int, then do that. If it's literally anything else, then we do that. And all of this and all of the recursive logic goes away. There we go. That's a bit better, I think. I will need to have import data sequence. In scope, and I will probably want to import a few things from it to have access to unqualified, such as this operator I've been using. Okay. Okay, that's a bit cleaner. Expand hasn't moved that much. And now I suppose, so add function, where do I do an add function? Right there, okay. I'm not going to touch this function for now. I'm going to assume it works the same. Except now this is no longer taking functions, this is taking a binary. And this contains the main address and the functions. Okay, so this is going to be wherever I have functions, I now have this. Other way around. There we go. And I will need to first why do I add function with a number? Yeah, this is why I'm introducing like the function and binary and new types, is because like this is a pair of int and pair of an int and image. That is not very clear. So the fold is using add function, which means the accumulator is this. But this is, so that's the f count. Why does it matter? Why does the f count matter? Oh, because I need to know how many. Okay, that makes sense. Okay. So that means here, this is going to change. Do I want to change this fold to be a statement add instead? I think it's fine to just for it to just be a fold. The only thing is, this is no longer images. This is now. No, actually, this is fine. This is images. However, this is. Well, first, functions is now a sequence. So this is now a sequence zip. And this is a sequence fold. Although this is probably just a regular one because I think fold is now generic over the over the traversable thing, so that doesn't change anything. However, here, this cannot just be that. It needs to also be start function at the beginning of the list of functions. Let's add this other operator to the list of things we import from sequence. And start function will be a generate start function call from the main address. Okay. Generate function, generate start function will be something that, given an address, which is just an int, will give me a sequence of instruction resolved, which is what is. I guess it needs to give me a function, I suppose. So it needs to give me a function. And generating a start function with main address. This is gonna be a function where I have the entrance count is gonna be 2. This is hard-coded. The function entrance will be 0. This is hard. Actually, it's 1. This is hard-coded. And the instructions are gonna be this is where we hard-code our main function. What does main do? It does a push address, well, push int of the main address. Because at this point, this is post link, so we know the address. There's no longer push address, it's just push int. And push int 2 first, which is the return address. In fact, it's an entrance first. Then we push 2 to be at the bottom. This one will be address 1, basically. Push int 2, which is the return address from after calling the main function. So we go back to into entrance 2, push int main address return, so that we call the main function, basically. And then the second entrance. And when we come back from main, it doesn't matter what shape the stack is like, we only terminate. So that's our start function. And this will introduce this terminating block for us without having to do it manually in GIMP anymore. Okay? That's all a tiny bit cleaner. And now this is just a fold of add function, so I'm not gonna change that. The big difference will be no, I guess it's the same. Except here, there's something that has changed. This seems to expect the image to contain yes, because I fmap generation function image. So that's not completely true anymore. Okay, so how basically what I'm trying to figure out is how do I avoid a pair of int image in this way, because that's ugly. Wait, am I... I should use a monad for this. I am giving strip height as an argument in my accumulator and it doesn't change. So that's really wrong. Because that means I could... Hmm. Okay, even if I don't use a monad for this, the strip height can be given as an argument first. Then that's the accumulator. Then that's the value of the thing. And then that's the image. And strip height can be given once. And doesn't need to be part of the result. So that's already cleaner because it doesn't change. And here I do a second, so I ignore the result anyway, so I can remove that as well. Which means this becomes just that. Okay. So this becomes... Hello, this evening is just a very low effort stream. I'm doing some cleanups. I did a cleanup of the linker, trying to improve it, and now I am doing some cleanup of the old assembly code, which is the one that generates an image based on the linked functions. Uh, while this was a cleanup stream, I've still done a tiny bit of work that's going to be useful, which is that I am introducing a new start function, which is this one, that does a proper entrance and terminate and everything to properly handle shutting down the program, and simply does a push of the main address on the stack and just calls the main function basically. So that's a tiny bit of an improvement, but it's mostly cleanups. The old linker assembly code is almost... Yes, I call it start. It is a not a name I have chosen randomly. But yeah, it is otherwise mostly a slightly lower effort stream. And yeah, the code for generating the image and doing the linking is almost a year old at this point, and a lot has changed since. So it's good to do a bit of a cleanup and harmonize it with the rest of the code base. One thing I'm trying to figure out here is I have replaced the old type with now this function thing that contains that. Do I want to make this perhaps some kind of... that's the output of the... That's the output of the linking phase. No, I suppose I could... I'm trying to avoid using a tuple is basically what I'm trying to avoid. But I guess it's not the end of the world to use a tuple. Maybe I can just give it a name. And maybe then I give it a name and a function image. Well, a rendered... how do I call this? This is a function with additional information. I'm tempted to do this where, in fact, here those are functions where the instructions are a sequence of instruction, but this is parameterized by I, the type of the instructions, which means the linker here, whenever I do return a function, this returns a function that uses a sequence of instruction resolved. Okay. And here in the assembly, where do I have function? So this will give me a function likewise, which still has a sequence of instruction resolved, and generate a function of the for the image will be a function. Just on that also for readability. There we go. That's going to be something that takes a function that still has sequence of instruction resolved as an argument, and will return a function still carrying the same information. Yeah, target function would not be a bad idea either. But where the instructions are now just an image. And this is going to be let f instructions equals this in function. That's going to be a problem. I can't do that. Can I do a thing? Does that work? Let's try. If I have a data type A that has a constructor name A and it has a type argument, and X is of type X and Y is of type int, and except in Haskell syntax, not in Rust syntax. Oh, because come on. Is it? Why is that so broken? Why don't I have... Oh, maybe if I do that, I'll have... There we go. No, because it still doesn't compile. That's annoying. Let's say, what do I have access to? Data b equals b. There we go. So now if I have a value z, which is an a of 0, which is an int, and, well, 0, x equals 0, y equals b, that should work. I don't have a show, but that's fine. Can I do z where x is now a string? What's the type of that? Yep, it's fine with that. Okay, so I can instead do, I have f, and I do image equals in f where the f instructions have been replaced by the image. Okay. That's a bit better than what it was, which means now here, add function, rather than taking here this whole thing, this int image, will be taking a function image as an argument. So that's a fold function thing. And that's the function count, I suppose. And that's my function info. It was named entrances. Okay. So function here, that's the image, that's the F instructions. And entrances here, that's the F entrance count or something. Yep. Oops. Okay, so that's a bit better. Have more hard-coded colors here. I'm sure it's fine. Now, the only thing I'm looking at is... okay, this is where the append instruction is. I might move it to where it's used. Okay, so that's not a big change. Okay, so that should be all for the cleanup of this part of the code. It's still not great, there's still more we could do, but we can still try to see at least if this compiles and what I've broken. And then we can try to see how the... Yeah, this is called binary now. We can see if we can still generate some images. This is called context. And I will need also the info. State no longer exists, it's called context. Make lenses not in scope because I forgot to import control.lens. Here I do a run state. I think run state gives me the result first and the state second. Am I wrong there? Oh, it's linear context anyway. Oh yes, of course, this requires a linker info. And a linker info is a separate thing from this. There we go. Okay, that's always good. It's a warning that we don't need to keep. Okay, section list. Sequence line scope. Maybe I don't actually need, since the from list of sequence is just the regular from list. CF no longer exists. Function entrance. Is it just function entrance? I think it is. Yep. Aha, no, so I need to be explicit about with the from list. Could I just import data foldable? Wait, no. Foldable has a to list, but from list is from GHC is list or something. No. Wait. Yeah, from list will either be the GHC one for the extension, or it will be specific to a type, and I might as well, in this case, be specific. And so from a list here that I want is a sequence. Okay. LS can no longer exist. This is context. Yes, I have probably LC here. LC everywhere. And there we go. Okay. I've made a change to the way the circular logic in the linker works. So this might result in fun runtime issues. We will see when this compiles. Okay, ambiguous occurrence 2. Oh, because lenses have those. Interesting. What do I use lenses for in this? Probably mostly the operators? Do I need lenses in this? I might no longer need lenses in this module at all. Just gonna remove them. Ah, I do need them. But maybe I can just be very specific. Use and uses is what I seem to be using. F is actually called function. Ah, yeah, there's a bunch of operators. Okay, so maybe I need lenses. And I'm gonna hide those. Okay. So now, so images is the wrong type. Because here I use a map which suggests that this is a list, which it isn't. So this is an fmap2 of this now. Wait, this is just an fmap. There's no need for map of fmap anymore. Strip height is no longer first of images. This is now it's no longer first. It is the entrance count, I think. Here I also have an old map of something. And this is... Okay, no, that makes sense. That's the entrance count. That's correct. And this is the maximum height, which is the maximum. I'm going to keep it aligned just for convenience. And I'm going to rewrite this as images on which I apply this. Which means here this is images on which I apply okay, that's a bit more complicated than that. So this is the maximum of fmap. I'm going to put an fmap here if I can't align things properly anyway. I am doing a... Let's get the instructions, which is now an image. and do the number of rows. And I'm keeping it under parentheses because I need to then do that. Okay. Is that correct? Let's see. Yes, and now I have changed the order again. I think entrance takes an argument in this form, but I think in the resolve instructions it is just a unit. That's the cost of having. So the problem is I have enabled the overloaded list extension in this file, which is very useful for a bunch of sequences where I just use a list literal and it creates a sequence for me. However, the problem here is now on this line where I do a for on something which is a list literal, there is no longer a way for the compiler to know the type of this because it could be any foldable that happens to have an isList instance, and there's definitely more than one in scope. So I am going to rewrite this as a replicate m of. I need to be careful. I think that's prev entrance plus 6 minus current row. Because this is going from current row minus 5 to this included. So this is prev entrance minus this, so minus current row plus 5 plus 1. So it is prev entrance plus 6 minus current row. And for all of those, I do an expand 0 blank template. Okay. And so now our main is broken, which is always good. ToList is no longer required because now I've made everything be a sequence instead. Okay, our cleanup compiles. That doesn't mean it works, but we can try. We can try stack run our Piètre compiler on the test file that we've been running yesterday. And that looks like an infinite loop, probably in the linking phase. Okay, so exactly where I suspected we might have a problem. So this is the problem. I wonder if I need this state to be lazy just to guarantee. Because it is otherwise a strict state, that's probably the problem. Nope, that is still broken. That is interesting. Because I've definitely made use. I've definitely made use of a. Oh god. I've definitely made use of a state whose output is given in a reader this way before. So I know this can work. Hmm. Okay, because if I go back to this is how it was before. This should work. The tilde makes it lazy. So by default in Haskell, everything is lazy. So every field of a record like this would be lazy. Every argument to a function is lazy. However, while this has a lot of benefits, in terms of the compiler being free to optimize and in terms of like allowing for weird circular things that are that only work because laziness, sometimes for performance it's not great. So there is a language extension that I have enabled, which is here in my default extensions. I have enabled strict data. And what that means is that now by default, unless I specify otherwise, all the fields in a record like this are strict, which means when I create them, they are evaluated then. Function arguments and everything are still lazy. Laziness is still there in the language, but when persisted to a struct, it becomes non-lazy. And tilde is the way to recover some laziness, to say, no, actually, this thing needs to be lazy. And yeah, strict if you want to like gain better performance with your Haskell programs, strict data is one extension and 80% of the work. Most things will work exactly the same, and you will have a pretty significant gain of performance. Because that's the big thing of Haskell performance. It's a bit harder to predict than in other languages with all the laziness and the everything. And having a bit more control over when things are evaluated, like with strict data, tends to be the way to go for improving performance. So if I go back to this and I change that to be back to being a linker context, and it becomes just uh, this, and I have to give it the hash map as an argument here. Which means I can probably rewrite this as run state of the action with initial state of this. And initial states in state therefore takes as an argument the hash map address int. Linker info no longer exists. This takes, yeah, that's all good. And here, this is no longer view, this is uses. Okay. Ha. That's interesting. Because now this is the same code as yesterday, more or less. Let's see, what have I changed? Let's see, so I had a monad lazy like this. My monad was a linker state like this, okay. I had initial state the same way it is right now. And I was doing a run state go of the initial state. I was doing the same thing. Hmm. That is interesting. Because I don't see a difference now with how this was. So, what's the issue then? There is one difference, however. I don't think it makes a difference, but in wrong file. In this file, here I do get this before anything else. That should not make a difference. Because current, yeah, this should be fine. Interesting. Let's actually test this assumption of mine. Because maybe I have a bug somewhere else, in fact. And let's go for some good old printf debugging. Only thing is, I'm gonna need this to have deriving show, deriving show, which is always good to have anyway. There is better ways to do this. GHCI is a pretty good debugging tool. Sometimes, oh, so it's the assembly that's broken. Okay, so I was trying to debug something that was absolutely fine. So I've broken the assembly. The linking is just fine. Okay, so always test your assumptions before debugging things. That means I could probably go back to the linking method there, and I could probably... I think that was more or less there. Let's try. Except here this is views, back to views. Since the problem is not in the linker, maybe I can keep the reader approach, which I find a tiny bit better. And in fact, I can. Okay, perfect. So I was trying to debug something that was not broken. I suppose that happens. So now it means I have something broken in my assembly. That's interesting because I haven't changed much in this. This is just a fold over a zip on the images. I wonder if it's my zip width here that's wrong. Because I haven't touched this function at all. So I'd be surprised if this one was different. Interesting. Let me think for a second. What have I changed that could result in something like this being wrong? This hasn't changed, really. Well, it has changed, but not in a way that would... I still think this is what's broken. So let's do a good old trace show m of here. Do I have the function name? I don't have the function name. But I can just do that of the expanded instructions. Let's import debug.trace and I'll see what's happening there. Line 73, 961 in fact. I misread this one. Expanded instructions, there we go. I don't even enter the first function at all. Because this generate function image is called on every function starting with the start function. So did I introduce something so utterly wrong there that it fully broke the generation? That's fascinating if that's the case. That is mesmerizing. So we don't even get there. Because the fold... Okay, so can I try this in GHCI? Yeah, I think I need to figure out where exactly this is happening. Because my assumption was like, okay, the fold here is restricted to the list here, which is bound by being this plus one function. None of those things are infinite, which is why I'm deeply, deeply confused. There is no infinite stuff in there. This is an infinite thing, but it is... Oh, god damn it, you're right. That's exactly it. That's absolutely it. See, okay. Yes, you're 100% right. This is the problem. Nothing else is the problem. See, when you have a list and you do that, that's an infinite list. So if I try to compute its length, that's never gonna be import data. Actually, I'm gonna just refresh stack GHCI now that it compiles. If I have this infinite list like this of numbers, if I try to do the length, it's never gonna return because of course that list is infinite. But if I zip this infinite list with a list of a known size, like this, that works. I'm actually just, this is a list of int. If I zip it with, god damn it, I have too many extensions enabled, and therefore the compiler is like, this could be any type that matches. It's fine. This is a string. When I zip this infinite list of ints with a finite list of strings, then the zip finishes infinite time because everything that is trying to zip beyond the smallest of the list is ignored. So that works. But what I have changed is this zip is now a zip of sequences, which means this thanks to overloaded lists, gets converted to a sequence, and a sequence is not an infinite data structure. So when I do implicitly sec from list of 0, that should, yeah, that does do an infinite loop. So that is exactly the problem. Now, the question is there in sequence as a result? Because this pattern of zipping with an infinite list of numbers to get the index is a very classic one. Does this thing, there is map with index and traverse with index, which is basically what I want. So this would be, well, except traverse with index. I guess I could use the fact that there is a monadic instance of. Is there a fold within? Oh, yes, there's a fold L with index. That's what I want. So I want a fold with index. Sorry, your comment arrived just after I saw it. I don't know if the lag of the stream. You might have sent it before I said it on stream, but yeah, I saw it as you were typing your comment. Why doesn't that convert the generator behind it? What thing? What do you mean? Do you mean the what generator do you mean? But yeah, full edit with index is what I want. I'm gonna do that in the meantime. And that means that add function needs to be changed to take. Oh, I need to be careful. So add function selects the strip height, and then it needs to take the accumulator, which is the image, the index. Okay. So I'm not sure what generator you meant being converted. Let me look at any other. Do I have any other list literal in there? Oh, that's just a matter of representation. The way lists are represented, it is trivial for them to be represented. They're not using a generator under the hood. They're just using unevaluated data. A list in Haskell, the basic list type, is just a type that has two constructors, the empty list or colon, which concatenates a value to the beginning of the rest of the list. As long as the rest of the list is unevaluated, it can be any expression that yields a list, including an infinite one. For instance, I could make L a list which is 0 behind 1 behind undefined, and that's a perfectly fine list of int. And I can absolutely do things such as take 1 of L, and I should get take, and I get 0. I get take 2 of L, and I take 0, 1. But the second I need to go further, take 3 of L, then I get an undefined. But this part of the list is not a special generator that generates the thing. It is just a list expression that has not been evaluated yet, thanks to laziness. Sequences cannot do the same thing given the way they are represented, because the internal representation of a sequence is a tree that keeps track of where the end of the sequence is at all times. As a result, to keep track of where the end of the sequence is, whatever the expression is that generates the list, it must have an end, which this doesn't have. yeah, this it's the thing of like you can see any expression as a generator in a sense, which is just this is how laziness works. An expression that has not been evaluated yet is just that. It is a generator for whatever the thing that you want to do, which means you can create an infinite list of ones by saying that it is one behind ones. And that works. That's an infinite list of ones. And if I take 10 of them, I get 10 ones. Because ones is an infinite list of thing, and it is constructed as one at the beginning of whatever this expression is, which is one at the beginning of. So every time you need more of this is evaluated, but it is just it is just an expression an expression of type list of int uh, that is lazily evaluated when needed. But with sequences, that doesn't work. Okay, that seems to compile now. Thank you, by the way, for pointing out the 0, when I was like, there's no infinite structure in this, because it was staring at me right in the face, and I was not seeing it. Okay, now that compiles. And we see what the binary looks like. I'm tempted to reduce some of the print because that is... that also works. But it's the same thing, basically. An expression of type list is a generator in a sense. Okay, now what I want to try is this should have created a new program file. Let's have a look. Nope, that is wrong. Hmm. No, that is just created right now. Why is it... Why does it have only 2 functions? I don't think that's correct. Something is wrong here. It does have the terminate here, so that's good. So that's our start function that has an entrance, a push 2, and a push 1, 2, 3, 4, a push 9? So the address of main is 9, but there's definitely not... Oh, I think I have something with the size of the image. I think main is supposed to be there. It's just missing. Okay. So that probably means in my assembly, I have something that makes... Here, I need to be very careful. I probably have something that looks at functions. Yes. So that would be length of the functions plus 1. Which I guess I can rewrite as a plus 14 here. But I think I prefer to have as a plus 1 here, because I am adding a function, which is the start one. Okay. Let's reopen this. I need to find a image viewer that doesn't do the same, that doesn't try to, or I should scale the images. Okay, so now that should work. So now we have ordered the functions. The hash map has put main there, basically. So now we have start at here pushes 9. Is that correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So it pushes 9 as the address to go there. So it then does all of the looping to get to this function, which is our main. And whenever it returns, it gets here where it's met immediately with a terminate block. Okay, so now we have a proper terminate block at the end of this. Um, the only thing is there's a lot of wasted space. My returns have a lot of wasted space. There's some wasted space there. The entrances are very verbose. I'm gonna try to see at some point if I can compress images a tiny bit more. I can also probably avoid, if I do a trace, basically, when I have a return here, the execution goes here, bounces here, bounces here, bounces here, bounces here, and go all the way at the bottom of the image to then come back here to the address selection thing. I could probably make it so that it turns left here directly, basically. That shouldn't be too difficult to make, and I could compress the functions a lot more. Another thing that I might want to change is currently the way the address works is I have an address on top of the stack, and this basically says, hey, is this address less than 2? Or greater than 2, I suppose. And if the answer is yes, then it continues here. Otherwise, it does -2, and it goes here, because if it's not greater than 2, then it must be 1 or 2, and so on. But as a result, if I have a function with a lot of entrances, this thing will grow quite a lot. So that's also something I might want to change in my address selection process. Okay, but that's still now a proper main thing. I kind of want to do a thing, since start is always going to be a very small function. Start is the only one that needs to be first because it needs to be the entry point of the function. I am kind of tempted to, because it's going to look better, go to linking. And here, when we link functions, before we visit them, we're going to sort them based on but if I do that, no, it's fine. Here I get a sequence from list of things. Does sequence have a sort? Sorting, it does. It has a sort on, that's even better. And I want to sort on function size, where oh, I need to be careful there. Oh, I need to be very careful. If I sort after I have done all of the addressing, it's going to be wrong. So it needs to be sorted before I do that. So it means, in fact, that I need to visit them in the order. That's a bit more complicated. It's a bit more complicated because I want to be able to know which one is main. Okay, I'm not gonna bother with that for now then. I am not going to bother with that for now. I think it's fine for the functions to be in an order that works. Let's try actually one thing, which I haven't tried, which I should have tried, which is to run verbose of our new program. And that failed immediately, which is bad. Oh, but I didn't do a trace. There we go. So when we return to we do get 8 with a return value of 2, and 2 is the address to go back to main. This is the address of the exit. Okay. So it is still working. Perfect. Okay, so that's some cleanups this evening. We've added binary, we've added monad here, a whole linking folder there. We've moved a few things. This deleted. And I might, in fact, remove that because it was a bunch of debug printf, where it just means main no longer compiles because I still have a to list here that's no longer required. So this should compile again. Oops, sorry, I hadn't seen your message. Give me 1 second. I'm gonna show you. If I do this with the trace image, that's gonna be slow as all hell, because now every step of the trace has to modify an image. So I might kill it because it's a few thousand steps. So I might kill it now. And if we open trace, oops. Oh, this program did not. Oh no, okay, that's the scale one. That's why. So you can see here, it pushes a 1 at the beginning. This might be a bit small. Let me zoom it. And let me check on OBS that this is still, yeah, okay, perfect. So push 1 here, it goes all around the image, does here a very basic rotation that resets the side selector to make sure we select the left side of this edge. Then this is where we do the address comparison. We go there at first, so the step 14 is there. If the address that was on top of the stack is this one, we end up on a 0, then we rotate and we enter this. Likewise, I'm tempted to probably try to simplify the entrance thing, which is a bit big right now. It doesn't have to be that big. It could probably be a bit smaller, but it works for now. This is the push 2, which pushes the return address before the function call, and 2 is this entrance. This pushes 9, which is the address of main, and then this is the return block that just exits this function. We've pushed 9 on the stack, so we go all the way there, we go back here, we go through this. 9 is this entrance. And this entrance is the start of our Fibonacci function that does a few things. It's of our main, sorry, which pushes the argument for Fibonacci, which is a push 5 here, and then push 10, which is the return address of the. That's something that an optimizer could do, actually. I do a push, then a swap. I could probably detect that and just do the pushes in the other order when they are hard-coded like this. I swap them so that the argument is above the return address in the stack. And oops, apology. This thing is not very convenient. Okay. So here, this is the main, this is the entrance of the main. We push the 5, which is the return address, push the 10, the 5, which is the argument, 10, which is the return address, which is going to be this entrance, and we swap them. So here, an optimizer could try to realize, whoops, we do push, push, swap. Maybe we just do the push in the other order. Then we go to with push 3 here, which is the address of this entrance, and that's the start of our Fibonacci function. This whole thing is organizing the stack and the values for the function and the registers. And the first thing we do is do a comparison of is it greater than 1 or not. And we didn't let it run long enough to meet the case where this flips the execution here, which is the end of our recursion. So we went through this phase that pops the stack, pushes a new address, and goes. The thing is, likewise, an optimizer that we will have at some point will realize that this push return goes to this entrance and just fall through, basically, and remove the return thing. But we don't have any optimization yet. So that's the cleanup. Now we no longer have to add the termination. Actually, I could go back here, make sure that this is visible on the camera. Let me scale this as much. Okay. I should actually let it run because we don't see it there. But this is where the execution terminates. Let me change something. I'm gonna change test pi fiber of 1 instead, which should be a lot faster to run. I thought I had removed the prints there. Oh well. Because now that should be a lot fewer steps. There we go. And so now we can see the fact that here the condition up. Here the condition was met, our if was met. So here we did a switch to switch to the other phase of the other side of this edge. So we bumped here rather than falling through here. And here at the end, when we come back to our start function, we fall through here. This does nothing, and this enter a thing that is trapped afterwards. A step 1 pixel move? No, not necessarily. The way Piètre works is one block of pixels to the next. For instance, here you can see that we go from this block of 9 pixels to this block here of other colors, and it is the transition in colors that dictates what instruction that is. So from this color to this color, it's the same hue but one step in lightness. That translates to a push instruction, and the size of the value pushed to the stack is the number of pixels of the block. For most instructions, so here this was a 2 pixel block into a other block that is just bigger. That color transition was also a push, but push of 2 because this was 2 pixels. All instructions except for push do not care about the size of the pixels, which is why for most of them that don't have a push, I just use a row basically in my function. But for pushes that need to be bigger values, I do like this is a push of 9 basically. Let me show you if I go back here. Yes, there we go. Lightness change, hue change. So a push is the hue doesn't change, but the shade got 1 darker. And if it's the darkest of all 3 possible in that shade, then it just wraps back to the lightest. Same hue, one lighter, so 2 darker is pop, and so on. Those are the 17 instructions. And yeah, exactly. A step is 1 block to 1 block. Well, except the interpreter also treats, so white we can just go through, and black makes the thing bounce. This interpreter seems to consider a step away from a block until an edge to be a step. So this would be a step, 31, 32, 33, 34, and so on. There is a subtlety, which is that there's 2 registers that the interpreter keeps track of, which is the direction that we are going. So here we're going down. We have encountered an edge, so we turn 90 degrees. We're going right, and so on. It's always 90 degrees in case it's blocked. But the other thing is, what side of the edge do we try? So when we are leaving this block here down, there's living we are living from this edge, but are we living from the leftmost pixel of the edge or the rightmost pixel of the edge? And that's also a thing that is flipped whenever something is like when trying to find a path through black pixels. That's also a thing that is flipped, and that is something that I use. Here, for instance, I force, when I do a rotate here to start a function, I block half the edge to make sure that we have that particular register set to the left. So left going down, so we are on this side of the block going down. And I make use of this because my branch instruction that we can see here, what my branch instruction is it sees a 0 or 1 on top of the stack and switches which side we are on based on the value. So if the value was 1, we switch to the right hand side going down, and so we leave this block here and we bump on the black thing and we leave. If this had been 0, this operation would not have changed which side of the edge we leave the block from. We would have left from this side and we would have fallen through. This is how I've implemented the branch block, basically. Okay, that's most of the cleanup I had in mind for this evening. I'm gonna put this back. Because at least now we have a proper termination thing. There's a few things I could do next. I could do some cleanups of the template of the generation, but I don't think I want to work on that next. I think one big next step will be figuring out built-in functions, so I can have print and so on and other big quote-unquote standard library functions that I can call from my program, so that now instead of doing this, I can do print of this and not have to inspect the state of the memory. That would be good. However, I think, yes, this is side effects everywhere. I think to do that, I will need first to probably, and I think this is what I'm gonna do next stream. What I'm gonna do is I'm gonna clean this thing, because this main that I've been using, despite having, vague usage and everything, it is absolutely debugging stuff. This is the main of our program. It is a complete mess. It prints a bunch of nonsense here in the terminal. I'm gonna need to start thinking about having a proper structure for this, because I have everything I need for incremental compilation, for multiple unit incremental compilation. Including persisting interface files, persisting object files. So I'm probably going to want to figure out the build system, in a sense, and the repository of interface and objects and everything to be able to do incremental compilation. I think that would be good. And have a clean compiler. That way I will replace this ugly main thing by a proper program. I think that's one next big thing. And when I have that, then I will have a notion of what is a precompiled module with its own interface and everything. And I can start providing, okay, here's the prelude or the standard library or whatever it's called, all the built-in functions. I will have a frame of reference for what their representation needs to be, which will probably be some kind of hard-coded, pre-compiled module in the build system. So that, I think, is going to be the next step. Another thing that could be good is continuing to translate more things from the IR. This IR is very, very rough. There's probably some things that need to be changed in it. And one thing I'm thinking of is handling of structs, because for now in the generation of the code, here we don't yet handle all instructions. Like we don't handle everything related to structs, like combine that combines several registers into a new struct, get field and set field. Those are not implemented yet, and they are important. So that's also a big thing that needs to happen. But for that to happen, it also means I need to figure out how to change a lot of those things to work. For instance, here I have, and not here in the monad as generation monad, I have this rearrange stack function that generates all of the instructions required to switch the order of the arguments on top of the stack so that they match what the next operation requires. Those are all assuming that the size of a register is 1, which will not be true the second I add structs, and whenever I add dynamically sized values on the stack will be even worse. I've been trying to think of like, do I want to implement pointers by using references to the base of the stack? This is probably doable. I've been talking to a friend on Discord about it, but I still think I don't want to do that. Dynamic, I don't want to implement a heap. I don't want to have to implement a heap in basic Pit instructions. So because I would have to deal with like fragmentation of memory and everything. Like it would be a nightmare. So I think I'm just not gonna bother with a heap. I'm just gonna have everything being dynamic on the stack, but that makes some of those functions have to be rewritten. Another thing I want to do, I don't know when I'm going to do this, I want to do some tiny bit of optimization. The bulk of the actual optimizations will be done on the IR, because that's where the LLVM IR like does its thing, because it's low level enough that it's useful. At the same time, it has enough information that it can spot patterns. But I will probably want to do a post-processing phase at the end of the generation phase to be like, oh, this jump goes to the address which is right after. Maybe I can do a pass-through instead and remove the return. Or I can notice that, oh, I do a roll followed by a roll of the same value, or I do a push followed by a swap. I can probably reorder those. So there's probably some ways to fix this, basically. Oh, so basically, some ways to do some optimizations there, I think. But that's where I want to go next. I need, I think, to think a tiny bit about how I want to approach those next steps. But that will be next week, I think. Let me just commit all of this. This is mostly linking and assembly. A cleanup. We didn't change anything. We added the start thing, I suppose, but beyond that is mostly a cleanup of things. Okay. I'm still not holding myself to very, very descriptive commit messages for now, that we're still in a extremely rough part of the project. When we have a 1.0 and we have a stable thing that we iterate on and we do features, then I will put a bit more effort into commit and pull a request and everything. For now, this is not a point where this is something that really matters. Thank you everyone for tuning in for this slightly lower effort stream. Have a good weekend, and I'll see you next week. Oh, and all of the recordings of this week are on YouTube. I've been better at putting stuff on YouTube immediately after streaming rather than doing it weeks later. I'll try to do this stream by tomorrow. Okay, see you everyone.